The simple question we want to see, we do it. We solve it in two different ways. The first way, just work on our data directly without doing any preparation work to organize the data. The second method, we spend our resource. So we use part of our resource to organize the data first. Then we work on the organized data and we compare the difference. So that's the idea. So let you see what's the difference. All right. Look at the question. Problem number 7. Element uniqueness problem. Given an array, definitely unordered. So I do not give you that order information, so we assume unordered. Question, how to check if all the elements are distinct? If all the elements are distinct, then your function should return true. Otherwise, false. That's simple. Okay. All right. So it's a simple question. Yeah. All right. But here we want to do it in two different ways. All right. Method 1. Method 1, brute force method. So don't do anything fancy. Just work it out. Okay. In a straightforward way. Brute force. So, all right. That means we do nothing to organize data, right? So don't do anything to organize data. Start your comparisons for checking. Compare the elements and see if you can find two of the elements share the same value. All right. So the preparation step, there is no cost because you do not need to do anything, no cost. Let me use a simple diagram. Here in this array, we have n elements. When we do the checking, we don't want to miss anyone, right? We don't want to miss any possible pair for the checking. So here's the idea. We want to cover all the possible pairs. For each pair, we want to check if two elements in this selected pair share the same value or not. Here, can you tell me how many total pairs you can find in this array? Total number of pairs. Anyone? So you can get an idea quickly. You can tell me how many pairs. All the possible pairs. We don't want to miss anyone. Okay? All the possible pairs. All right? Yeah? All the possible. So here, you need to recall in our discrete math. So this is a simple counting question, basic counting question in our discrete math. Discrete math, how to form a pair. You need two elements, right? You need to select two of the n elements from the given array. So it's a combinatorial number. N select n choose 2. N choose 2. Combinatorial numbers. So let's recall. So the counting problem, because when we select pair, the order is not important, right? We don't worry about the order. So order not important. So if you use the combinatorial notation, that's n choose 2. This notation. So that is 1/2 times n minus 1. Right? That's the total number of different pairs you can find. So that means you need to do this many comparisons. You need to exhaust. So for here, I'm talking about the worst case. Worst case, you need to go through all the possible pairs, right? The best case, you only need to do one comparison, the best case. Worst case, all these pairs. All right, so here, yeah, the specific comparison is like this. Here, I can also show you. We need to follow the order because when you write a program, yeah, so this is just give you the idea. So how many pairs you need to, how many comparisons you need to do, okay? So this gives you the number of comparisons. Although we know worst case, right? Yeah, not the best case. All right. But if you are asked to write a program to do this kind of checking, you need to write a code, right? Yeah. You need to write, for loop, nested for loop to do the checking. Yeah. So here, so we need to understand the implementation details, how to do the checking in our code. All right. Yeah. So when we select the first element, we want to, fix the first element as the first component in our pair. Yeah. Pair. Two components in a pair. So we fix the first one. First one, yeah, we select it. Then the second pair, we go through all the remaining elements, right? All the remaining elements. There are n-1 remaining elements. Okay? Yeah. So we should cover all of them. Yeah. That's the first round, first scan of the array. Yeah. All right? But after that, we need a second scan. Okay? The second scan, we select second element as our first component in the pair, in the current pair. All right? Yeah. And then we fix it. For the second component in the pair, then we go through all the remaining elements in the array after the current element. So n-2. Yeah. Not before this element. Okay? Don't do it before this element, because we already covered it before, right? Yeah. So we don't want to do the redundant comparison. Yeah. So don't go back. If you go back, because we complete that comparison in the first round. Yeah. First scan. Yeah. So then second round. Yeah. Then third round. And so keep doing. The last round, we only do one comparison on the last two elements. So if you write a code, you should do the processing in this way. Okay? Nested for loops, outer for loop, and inner for loop. Yeah. All right. And the efficiency, best case, one comparison. Because best case, we are very lucky. The first two elements you check, they happen to be the same. So then you're done. Okay? Yeah. Yeah. So your function can return true or false based on the definition. Okay? If you set uniqueness as true, so that false, because not unique here. Yeah. All right. The best case. Worst case, you're not very lucky. One of the worst cases, the last two elements happen to be the same. You need to check all the possible pairs. Yeah. But there is another one, distinct case, right? Distinct case, you need to check all the possible pairs. Okay? So other than this, non-unique case, the distinct case, that's the worst case. Yeah. All right. So this is our method one. Yeah. Brute force method. Yeah. The efficiency, worst case efficiency, this formula. Yeah. All right. So let's leave it aside. Our next method, we want to do slightly different. Yeah. All right. Average case, yeah, so you can think about, but for the average case, remember we did a linear search question. In that question, when we do the average case, we need assumption on the probability, right? So here you also need that probability, P, okay? Yeah. based on the history data, you do statistics, so you need to estimate that P. Then you can calculate the average case efficiency. Yeah. All right? Yeah. So here I do not go, that details. Yeah. All right. Our method number 2, this time. So we are willing. So before we start our comparison, so we are willing to do some preparation work. This preparation work, we invest our resource on some important task. So organizing the data. Yeah. Organizing the data. How to organize the data? Yeah. In this question, very simple. Yeah. Sorting. Yeah. So we sort the given array. Okay? Sorting. Okay? Yeah? Yeah. Sorting, we know, that's not cheap. Yeah. Sorting. You need to do a lot of work. Okay? Sorting, that task is not cheap. So you need to spend quite some resource on sorting. Okay? Yeah. All right. Sort the array first with certain cost. The question, how much cost? Because that cost important to help us make our decision. If the cost is too high, then we don't want to spend that much cost. Okay? If the cost is under control within some acceptable range, then we can do it. Yeah. So we want to see that number first. Yeah. The comparison number, the cost number. Okay, all right. So here I use our later result. So this sorting cost, here I give you the formula n log n. N log n, this result, we haven't learned this result. Yeah. So when we move to module 4, we will learn this result. Module 4. After our midterm, we will learn this result. Okay? Yeah. But here, because we need to use the sorting process, so we need to borrow this later result. We apply the best sorting algorithm here. Okay? We don't want to apply some bad sorting algorithm. Okay? Like selection sort. We did a selection sort. That one's pretty bad. Yeah. If you apply selection sort, then you waste too much of your resource. Yeah. So not acceptable. Okay? So that method not acceptable. So you want to use the best possible sorting algorithm. Yeah. Here I can give it a name. Yeah. Quick sort. Name. Pretty quick sort. Okay? So here, we will learn in module 4, quick sort. Okay? Quick sort will give us, this much estimated cost. Okay? All right. Yeah. All right. This is our preparation step. Okay. All right. After that, now our data is organized in an ordered array. It's organized data. Okay? So then when we work on organized data, we hope we can greatly improve the overall efficiency. That's the idea. Okay? The data is ordered. Yeah. Now I ask you to check. So assume this array is already sorted in ascending order. Now I ask you to check, to do the comparisons, to tell me if all the elements are distinct or not. Can you do better than before? Organized data. Yeah. So definitely much better, right? Yeah. Because this time you have a nice property you can take advantage of. A good property. So what property? Okay. Because this time you only need to do adjacent comparisons. That's enough, right? Yeah, sorted. Adjacent comparisons. Okay? So when you select pairs for comparison, you only need to select two adjacent elements. You do not need to cover all the possible pairs, right? Yeah. All the possible pairs, too many. Yeah. So, yeah. From the, combinatorial number, all the possible pairs, and choose two, this many pairs. Yeah. This pairs we call the global pairs. Global pairs. Okay? Yeah. But here, when we choose adjacent elements, we only look at the local pairs. Local pairs. Here you can see what we are doing here from global processing to local processing. Global processing, very expensive because too many cases. Local processing, much cheaper because we reduce the total number of cases. We greatly reduce the total number of cases to be considered. Okay? Yeah. Here I can ask you, how many adjacent pairs? Yeah. The pairs formed by two adjacent elements. So can you tell me that number? Adjacent pairs. Do the counting. Okay? Count quickly. Yeah. Adjacent pairs. How many? Yeah. Yeah. Here I couldn't see the response from the Zoom side students. Yeah. Later I need to, show me a screen. Yeah. Here, let me look at my chat message here. Yeah. All right. Anything? Yeah. Yeah. Nobody respond. Yeah. All right. So let me tell you. N minus 1. Yeah. N minus 1. Okay. The first sorry. Yeah. Something not quite. You can see after I check the chat. Oh yeah. Yeah. So I get it. All right. So you can see first adjacent pair, second adjacent pair, third, and so on. Last adjacent pair. Okay? The total number, n minus 1 adjacent pairs. Okay? If we write a pseudocode, you can see we don't need a nested for loop. We just need one simple for loop. Okay? So you can see this many comparison versus if you do global comparisons, you need, 1/2 n squared, approximately. So here, because remember, we frequently use approximation. Here, if we do approximation, we like to, drop that minus 1. Okay? 1/2 times n squared. That's a good approximation. Okay? Drop that minus 1 to make the total, the whole form look simple. Okay? 1/2 n squared versus here we also do approximation. We just keep that n. Okay? Yeah. We drop that minus 1. So you have n. You compare n and 1/2 n squared. That difference. So you can see, yeah, that difference. Yeah. All right. Yeah. So definitely that difference is big. That difference is really big. Okay? It looks like our second method much better, right? Yeah. But don't make your conclusion that fast. Yeah. Because you spend a lot of cost in your preparation, right? You need to count that preparation cost. Okay? You need to count that preparation cost. Okay? Yeah. So you need to combine, add up these two parts, the cost of these two parts. Then you can do fair comparison, right? You can only compare this part 2 with total cost of method 1. That's not fair. Okay? All right. Oh, sorry. Oh, yeah. For the comparison, we need to go to part B. So that's why, yeah, we complete this topic. Yeah. Comparison, we move to part B to do the comparison. Yeah, not here, yeah. Because we need a mathematical tool to do it. Okay, all right. So let me finish part A. Well, let's go to part B. Yeah. All right. Yeah. Part B. Yeah. This is part B. All right. Yeah. Change my pen color. All right. Yeah. Okay. Yeah. The topic, two topics in part B: growth functions and brute force method. Yeah. First, concept. We need to learn the growth function concept. Yeah. P.1, introduce growth functions. Yeah. All right. Our goal, yeah, so because we need to look at what's the goal of this module, part 2. We need to learn how to do analysis of algorithm efficiencies. So we need some tools. We need some, concise method, notations to help us study algorithm efficiencies. Yeah. One important concept, growth functions. Yeah. So let's study this concept here. All right. Formulas between running time and a number of basic operations. Here we need to do the algorithm efficiencies. Yeah. How to measure algorithm efficiency. Yeah. One way, straightforward way, running time. Okay? We use running time. So when you run your algorithm, write a program, run it, then you clock it, you look at the response time, running time. Yeah? So in your project 1, you need to do that. Okay? Project 1, you need to display response times of 3 algorithms on screen. Okay? Yeah. Yeah. In our requirement. Yeah. So that's one of the measures. Yeah. Second one, yeah, because that measure not stable. So we learned before. Yeah. So that running time, response time measures not stable. So we want some stable measures. Yeah. The stable measure, number of basic operations. This one is stable. This measure is stable because it does not rely on your hardware, software. Always we have this fixed number. After you find an algorithm, this number is fixed. Okay? Yeah. So number of basic operations. Yeah. All right. Here, notation for the running time, we use this capital T function, T of n, and the data size. Yeah. T of n, yeah, we represent the running time function. Yeah. Then, for the counting number of basic operations, we use this capital C counting function, C of n, counting number, yeah, C of n. Yeah. And these two functions should be related in some way. Yeah. So closely related in some way. Yeah. All right. So if you want to ask what's the meaning of basic operation, yeah. So we learned before. Okay, we learned before. Yeah. Here I just recall, yeah, the meaning. Operation contributing the most to running time. Yeah. Yeah. Remember, in our polynomial evaluation problem, we have 2 operations: yeah. Addition and multiplication. Yeah. Addition, multiplication. And we know multiplication contributes the most. So we treat multiplication as the basic operation. Yeah. Yeah. All right. Then we also need to make assumption. Execution time of one basic operation on your current machine. Yeah. Current machine. So there is a little c constant. Little c sub op. Okay? Yeah. So that's another constant. Yeah. This constant depends on your current machine. Yeah. All right. Then we have a relationship. Yeah. Yeah. The formulas describe the relationship between T of n and capital C of n. Yeah. All right. Yeah. Approximately, so we can use approximation formula. T of n approximately equal to C, little c op constant multiplies capital C of n. That's the relationship. Yeah. Yeah. Approximately equal. Yeah. Then here, the constant multiple, we use a constant multiple to connect these two functions. Yeah. All right. So that's the relationship. Okay? Yeah. All right. We can say these two functions are proportional. Yeah. Proportional. Yeah. Okay. Yeah. All right. Yeah. Yeah. And we know that C function, we can handle C function easier. Yeah. Easier than T function. Yeah. Why? Because we don't need to write program, right? We can calculate the C function formula without writing program, without do experiments. We can get C function. Yeah. To get T function, you need to write the program, then you need to do the testing, then you can, collect the data for the T function. Yeah. All right. Approach, yeah, here. Now, our goal, yeah, so we always monitor our goal, okay? Our goal, we want to study the efficiencies of the algorithms. Yeah. Yeah. So when we study efficiencies, yeah, we know our algorithm efficiency function, usually it's a formula. The formula could be relatively complicated. Yeah. Could be relatively complicated. Yeah. But we want to simplify. Yeah. When we do the comparison, we want to only compare what? Compare the dominant terms. Remember I introduced the dominant terms before. Yeah. Because when we use the dominant terms, we can simplify our formulas. Yeah. Here, we ignore unnecessary details, only keep the most important, the term with biggest contribution. We call it a dominant term. Yeah. So we only keep the dominant terms when we do the comparison. Yeah. All right. Yeah. Here. But in our formulas, yeah, so there are many constants. Yeah. Yeah. Constant in our formulas. Yeah. Here, the question, how do we handle those constants? Constant in different places. Yeah. We need to see how to handle those constants. Yeah. All right. And how to ignore the minor terms. We also want to do the right way. Yeah. Right way to do the simplification. Yeah. All right. So here, let's look at these two ratios. Yeah. The first ratio, left-hand side, capital T of 2n over capital T of n. Yeah. Then, based on this formula, right-hand side, we know the little c constant can be cancel out. Little c up. Numerator, denominator, we can cancel out. Yeah. So the right-hand side, you can see it is capital C of 2n over C of n. Yeah. What's this? Yeah. Here, let's look at the meaning of this ratio. What information does these two ratios tell us? Okay? Yeah. Yeah. Here you can see the ratios. Yeah. You can get a function increasing information, right? Yeah. Because the numerator t of 2n, you double the size. You double the data size, right? When you double the data size, the function number should be larger, right? The function increase should be larger. Yeah. Because when you calculate a problem with larger size, yeah, in general, you need to use more time. Okay? So the function number is larger. Then, how much larger? You want to get an idea. How much larger? So you take the ratio. Okay? Yeah. So you use the original function, t function, as the reference base, okay? Comparison base, yeah, reference. Yeah. Then you use the same function, but you double the data size, okay? Double the problem size. Okay. Then you want to see how large is the ratio. So that ratio, you can feel, gives you the rate of increasing, right? Some rate, yeah. Increasing rate. Yeah. You can call it increasing rate. Yeah. Here you can see if we use the ratio of this format, yeah, same format, yeah, ratio like this, to represent the increasing rate for a function, we can see, yeah, these two functions, t function and the C function, they have the same increasing rate. Okay, same increasing rate. Yeah. If we understand in this way. Okay, yeah. All right. That, yeah. So this property, so this is, yeah, this new property discovered. Yeah. So we want to use the property like this to help us understand the efficiencies of the algorithm better. Okay, yeah. All right. Yeah. Here, double the input size. Yeah. You may ask me, why not triple, right? Yeah. Because double convenient, right? Yeah. If you want to use triple, yeah, it's fine. Yeah. But double. You know, most people like to use the double. Okay? Yeah. All right. Yeah. Yeah. So this ratio gives us the increasing rate. Yeah. Pretty much increasing rate. Yeah. All right. Next, introduce the growth function concept. What's the growth function concept? All right. Yeah. Yeah. Question. What is the major term in an efficiency function? Major term, minor term. Okay? Yeah. So let's review a little bit. Yeah. This major term, dominant term. Okay? Yeah. All right. The selection sort, let's look at the efficiency function for the selection sort. Yeah. All right. Yeah. So this is the efficiency function. Okay, the efficiency function. Now, we want to write it in two terms. The first term, much larger than the second term. The first term, we call it a dominant term. Okay, yeah. The second term, minor term. Okay, yeah, minor term. Yeah. But if you want to ask me why you call it a dominant term, yeah. So here, I need to look at the time. Yeah, all right. Yeah. If you want to ask me why you call it, so the first term dominates the second term. Yeah. here we need to use a reasonable calculation to see that dominance, how dominant it is. All right, let's take the ratio between these two terms. We use the first term over the second term, then look at the ratio where n goes to infinity. We look at the limit. Here we need to use the calculus knowledge. All right. After cancellation, you can see the limit is n. N function goes to infinity. That's infinity, right? So if you ask me how dominant, the ratio goes to infinity. Now you have no problem on the dominance, right? No problem. Because the ratio goes to infinity. Okay? Then the second term can be ignored. This time, if I ask you to ignore, throw away the second term, do you feel comfortable? Because very little. Think about, you have total amount of some quantity. If you ignore 1% of it, do you feel acceptable? 1%. Here, much smaller than 1%. Because the ratio, infinity. 1%, we know 100 to 1 ratio, right? If you throw away 1%, the ratio to be thrown out, 1 of 100. But here, the ratio infinity, much larger than this 100 to 1 ratio. Infinity. Okay? Larger than 1,000, larger than 1 million, larger than 1 billion. Then, if you have 1 billion, do you feel comfortable to throw away 1 of it? Ignore 1, just the 1 of 1 billion, right? No problem. No problem. That's the reason we can ignore minor terms. Because the ratio is infinity. Okay? All right. So that's the how dominant, why we call it a dominant term. The second, when you look at this dominant term, there is this 1/2 coefficient. Leading coefficient is 1/2. Okay? Constant. It's a constant. But we want to do further simplification. So this 1/2 times n squares. We still want to do another round of simplification. So we drop that 1/2. We only keep the n squared. Looks much more simpler. But the question, why you can drop that 1/2? Okay? Why you can drop that 1/2? Here I want to explain why we want to further simplify our dominant term by dropping the leading coefficient. The reason is this. What do we want to do? So here. So we want to study algorithm efficiencies. Okay? But when we study algorithm efficiencies, we need to work on a large number of functions, right? Efficiency. Algorithm efficiencies are represented by their functions, efficiency functions. So we need to study a large number of functions. When we study those functions, we want to do one important thing: characterization. We want to do one important thing: characterization of those functions. Characterizations on those efficiency functions. Categories. How do we use different categories to represent all those functions? So we want to define the categories in some good way. Good way. Yeah. Yeah. So, but how do you, so what is a good way? Yeah. Yeah. Here. Yeah. First, we want to make the category big enough. Yeah. Not too small. Too small. For example, you know, and put a category n plus 1, you know, difference too small. Too small, you're putting two different categories. That's not good, right? Yeah. So for a good category definition, we want to make the difference between two categories should be big enough, okay? Not too small, okay? So here the difference between two categories, too little, okay? So that's not a good characterization way, okay? Yeah. So we want to make the difference big enough. Yeah. Here, we want to drop this 1/2, yeah? And we want to use n squared to represent the category, okay? N squared enough to represent the category. If you have 1/2 n squared, we put in the same category, not different category. Because the difference is you just scale it, right? You use a constant to scale the function. Why we want to put it two different categories, right? Yeah. One function, given a function, we can multiply a constant number to scale it, okay? Yeah. When we scale a given function, we want to put them in the same category. That's the idea, okay? The same category, not different category, okay? You just scale it, okay? Yeah. All right. So based on that consideration, now we drop the leading coefficient. We only keep the n squared, yeah, as the representative of the category. Okay, this n squared is the representative of the category we select for efficiency functions. Yeah. All right. Then, so this function we call the growth function. The definition of the growth function. Yeah. Yeah. After 2 rounds simplifications, okay? The first round we drop the minor terms. We only keep the dominant term. Yeah. The first round simplification. Second round, we drop the leading coefficient of the dominant term. So then, the remaining part, that's the growth function. Okay? That's the definition of the growth function. Yeah. Why we use growth functions? Yeah. Because we want to use growth functions to define different categories of our efficiency functions. Yeah, all right, so now, so let's look, next topic at B.2, compare growth functions. Yeah. Now, we want to do comparison. How do you compare two different growth functions? Yeah. We know each function has a growth function. Yeah. Yeah. We just solved that element uniqueness problem. We have two different solutions, solution 1 and solution 2. That means we have two growth functions. Yeah. The first one comes from solution 1. The second function comes from solution 2. Now we want to compare these two growth functions. Yeah. Which one increases faster? And which algorithm is more efficient? So we can answer questions from this comparison. All right. Now compare two growth functions from our previous question. Yeah. Which method is better? Method 1, the worst case efficiency, the function is 1/2 times n minus 1. Yeah. And the second method, the worst case efficiency, sum of two costs from two steps. The first term from the preparation step, sorting, so n log n. Then the second part, n minus 1 from local comparison. Okay? Yeah. Yeah. All right. So the growth function from the first efficiency function n squared, and the growth function, when you look at the growth function of the second efficiency function, we cross out minor terms, right? We cross out minor terms, right? The first step. After that, yeah, leading coefficient already 1. Yeah, so we keep it. Yeah, n log n. Yeah. So you can see after we extract growth functions from these two efficiency functions, their forms much simpler, right? Yeah, their forms much simpler. Okay. Now, let's do comparisons on these two simplified functions. Yeah. All right. We still take the ratio limit of these two functions. Yeah. So we can do cancellation. Yeah. After cancellation, we need to calculate the limit. When n goes to infinity, yeah, the ratio n over log of n. Yeah. All right. So here the log of n, yeah, we didn't specify the base, yeah. So we can consider a general base a number. A is a constant greater than 1. Yeah, a some constant greater than 1. Okay? Yeah. Very general here. Yeah. All right. And we can say this ratio is infinity, n over log n. This ratio is infinity. Yeah. Why this ratio is infinity? Yeah. Let me explain a little bit. Yeah. First, one way to see this ratio is infinity, yeah, we can use some substitution to tell us to look at this ratio in a different angle. Yeah. So we do variable substitution. Yeah. Because this log function, we feel this log function is a little hard to handle. Yeah. So we want to use a new variable to represent this log function. New variable u. Let's introduce a new variable u equals this log base a of n. Then we can write n in terms of u by definition of the log function. N equals exponential function a to the u. Exponential function. Okay? Yeah. All right. If we do substitution, we use u variable to replace n variable, then our original ratio, we can remove the log function. So you do not see the log function anymore, right? So your new ratio becomes u goes to infinity, you take the limit, exponential function a to the u over u, this ratio, okay? So you view the ratio in a different angle this time. In this new angle, you compare exponential function. Numerator is an exponential function, a to the u, with a greater than 1. Okay? The base of the exponential function is strictly greater than 1. Okay? Yeah. Then, how do you see the ratio goes to infinity when u goes to infinity? Yeah. Yeah. Because we know the increasing rate for exponential function much faster than polynomial function, right? The denominator is a polynomial function. And we know there is a property for the functions. So this property is an exponential function dominates any polynomial. Yeah. Yeah. Exponential function, but you need to make sure your exponential function must be with base greater than 1. Yeah. Otherwise, you don't have this property. Yeah. When the base greater than 1, yeah, so any exponential function dominates any polynomial. Yeah. Okay? Yeah. So that's some property of functions. Yeah. Although you can prove it. Yeah. Later we will prove it. Yeah. But many people know this fact. Okay? Know this property. Yeah. All right. Yeah. Next. Now we want to do rigorous proof. We want to do rigorous proof. If if you try to understand, so you may not use the rigorous proof. Here we want to use rigorous. So we need to borrow a powerful tool in calculus, L'Hopital's rule. So this L'Hopital's rule in calculus 2, you learn this tool, powerful tool. Okay? Yeah. Here we only use this special calculus tool from calculus 2. Okay? Yeah. So don't worry too much. We only use once. Yeah. All right. Method 2. Now this time we use L'Hopital's rule to calculate the limit of ratio of two functions. Yeah. L'Hopital's rule tells us when you calculate the ratio of two functions, you can use the ratio of two derivatives of these two functions to calculate the limit. Yeah. So that's very nice. Okay? A derivative, yeah, to calculate the limit. Yeah. All right. But there is a condition. There is a condition. Yeah. Yeah. The condition is the two functions in this ratio should be indeterminate form. Yeah. Indeterminate forms. Yeah, because you have many indeterminate forms. One commonly used indeterminate form, infinity over infinity. Okay? Yeah. When your variable goes to infinity, the numerator goes to infinity, and denominator also goes to infinity. Yeah. This is the first form of indeterminate form. 0 over 0, another commonly seen indeterminate form. Yeah. And there are others. Okay? There are several other forms. Yeah. For example, 1 to the infinity. Okay? Your base function goes to 1. Yeah. And your exponent function goes to infinity. Yeah. That's indeterminate form. Indeterminate means it could be anything, right? Because indeterminate. It could be any possible numbers. It's indeterminate. Okay? Yeah. And infinity to 0, right? Yeah. Look at that, indeterminate. Yeah. Yeah. There are many indeterminate forms you can consider. Yeah. All right? Yeah. And you can also, infinity, you can also consider, yeah. So, yeah, basically the answer is indeterminate. Okay? Infinity minus infinity, right? It's also indeterminate. It could be anything, right? So you have a lot of different indeterminate forms. But for this class, we only consider the first indeterminate, infinity over infinity, indeterminate form. Okay? Yeah. All right. Then let's do the calculation. Yeah. This time, because it is an indeterminate form. Yeah. When u goes to infinity, the numerator goes to infinity, denominator also goes to infinity, so it's an indeterminate form. So then we can apply the L'Hopital's rule. Yeah. When we apply the L'Hopital's rule, we can take the derivative of numerator and also derivative of denominator. Derivative of denominator, that's 1. Yeah. Derivative of u is 1, right? And the derivative of the exponential function, yeah, we have the formula. Yeah. Natural log of a times the original exponential function. Yeah. All right. After this step, then this new ratio, we can see its limit immediately. Yeah. Because other than the constant, we have the original exponential function. When u goes to infinity, the original exponential function also goes to infinity, so the whole ratio goes to infinity. Okay? So in this way, when we apply the L'Hopital's rule, we can rigorously calculate the limit of two growth functions. Okay? Yeah. All right. Yeah. Yeah. But make sure a must be greater than 1. All right? Yeah. Yeah. But when you do calculation like this, there is one technical problem you need to consider. Yeah. Because otherwise, if you ignore this technical consideration, your proof has a hole. Your proof has a hole. Yeah, not very rigorous. Okay? You miss something. Okay? You miss something. Yeah. So what's that? Yeah. So let me talk about this question. Then we are at a break time. Okay? Yeah. All right. The problem is the ratio of our two original growth functions. Look at the variable. Variable n number, we call it discrete variable. Because n number, you only take discrete values, right? 1, 2, 3, 4, discrete values. Yeah. So when you use the discrete variable, then the derivatives of those functions are not defined. No definition for the derivatives. When you consider derivatives, you have to consider functions with continuous variables, not discrete variables. Continuous variables. Okay, all right? Yeah. So for that reason, we should do conversion. We should convert discrete variable to continuous variable. So we convert n to x. Yeah. Here, x, we make it continuous variable. It can take any real numbers. Any real number. Okay, all right. Then, when we work on the continuous variable, we can apply L'Hopital's rule. Because their derivatives are well defined. Their derivatives are well defined. Yeah, so if we use their derivatives, no problem. But if you take derivative on these two functions, you have a problem. Not rigorous. Okay? Yeah. Not rigorous. Yeah. All right. Yeah. So then, after we take the derivative, yeah, so do simplification, yeah, the constant, natural log of a, it's a positive constant, yeah. Then multiply variable x, x goes to infinity, so the whole thing goes to infinity. Okay? Yeah. So the ratio goes to infinity. Yeah. Yeah. All right. So then we have no problem. Yeah? So no problem applying L'Hopital's rule. Yeah? So we get around that problem. Okay? Derivative problem. Yeah. All right. Let's take a break. Yeah. So